Okay, well, welcome to a new series, or what I think is going to be a new series that I'm roughly calling Crate Digging. Today we're going to talk about GlTF, and specifically we're going to dive into the bevy GlTF crate. If you're unfamiliar with bevy, bevy's a refreshingly simple data-driven game engine built in Rust. It's free, it's open source, you don't have to pay for it. It has really good support for programming things, if that's your vibe. And today we're going to look at a specific crate in the bevy collection of crates called bevy GlTF. So GlTF, for those that don't know, is a file format that we'll get a little bit more into, but it sort of allows you to store things like meshes and materials and the positions of them and scenes that are collections of them, as well as a whole bunch of other stuff. So at the very, very, very basic, there is a GlTF file format. This GlTF file format is a JSON-based representation, as you can see here. It has a number of things inside of it that we'll talk about in a second. This GlTF file in particular was exported via Blender, which we'll get into more in a second as well. But you can see here that there are nodes. In this case, I had an empty inside of Blender. It has some extra data, and all of this is stored inside of a JSON file format. That is true whether you have a GlTF or a GLB extension here. There is a GlTF specification that you can go read. I do not personally find it super helpful to read all that much of it, so we won't be spending that much time in the spec today, especially since our goal is to actually look at the bevy GlTF crate. Now, there are some nice things in the spec, such as this document right here. And you should already start to see some similarities. There was a scenes key in our GlTF file. There's a scene type in this document. So you can store things like scenes, which can be collections of arbitrary amounts of nodes. Nodes can have cameras. You can do animation and skinning for bones and what meshes they should affect. We'll talk a little bit about accessors and buffer views in a second. But there are also meshes and materials in here, images, textures, how should you sample those images and textures, and a whole bunch of other data. So the core idea here is there is a bunch of JSON data, and then there's also a bunch of binary data. And that binary data is typically things like vertex positions, vertex normals, anything that is like vertex data or lists of indices and things like that. So given a pretty typical startup for a Blender scene, that is, we have here a cube, a camera, a light. Inside of this cube, we have a mesh. Inside of that mesh, we have a material applied to it. If you want to look at these things in the right-hand side here, you have to use this vertical selector. So this orange one is the cube object, and this green option here has some details about the mesh data. We'll get into that. We're just going to export this for a moment. The first thing you see is that well, maybe not the first thing you see, but one of the options here is the format. That's either GLB or what is called GlTF separate, which is a GlTF and a .bin file and a set of textures. So if you were using images in your Blender scene, you can export to GlTF and either combine everything into one GLB file or separate it out on disk. That would be, the GlTF would be JSON, the .bin is all the binary data, and then you have a bunch of textures as images on your disk as well. Since we're talking about the contents of the file format, I'm going to use .gltf so that we can actually read the output. And we're going to go into my little GlTF showcase directory here. I'm going to name this something like that's not how you spell video. That's not how you spell video either. Video.gltf. Remember, I'm doing GlTF separate, and I'm going to hit the export button. So if we go back into our little project here, we're going to get out of this demo GlTF and look at our video GlTF. If we look at the .bin, you'll notice that it's not displayed. That's because this is just like packed binary data. It's like a bunch of loose F32s and other things like that. Loose is a bit of a loose term, but if we look at the contents of this GlTF file, because understanding the file is important for understanding the bevy GlTF crate. That's why we're going over this. You can see things like scene 0. This is an index. So scene index 0. What is an index into? It's an index into this key called scenes, which happens to have one scene in it. That is called scene, which has a number of nodes. So if we look back at our Blender scene, it's called scene up here, and we have some children inside of our scene. So if we look at these nodes, those are more indices. In this case, it's 0, so we go down to nodes, and index 0 in nodes is a cube. That has a mesh of 0, so we go down to the meshes. If we go into the meshes 0, this object is a cube with some primitives. These are attributes, indices, and the material that's being used. This material is another index. So we can go back up to the materials array and look at this. This is the material that is being used on this cube. In this case, it's a PBR material. It's pretty well defined. which is what allows us to take a material that is a PBR material inside of Blender, pass it through GLTF like this, and then use it in Bevy as a standard material. If you had more options here, more things would be here. But in this case, we just kind of had this like base color of like white-ish, 0.8, 0.8, 0.8. Right? You'll see there are names on basically everything because it came from Blender. That isn't strictly speaking necessary. And if we go back into these primitives, we can look at the attributes, which are interesting as well because that relates directly to this .bin. And we've got position, normal, and text coord 0, which are basically like the UV coordinates. We've also got indices, right? So these are all indexes too, but these are indexes into these accessors. So if we start thinking about the cube and the vertex positions of that cube, we can take this index, which is 0 in accessors, and we can say this is the accessor for the data in the binary buffer for our cube vertex positions. And what does that mean? Well, we have this cube here. If we look at, if I don't rename the scene accidentally, if we look at the data here, the dimensions are 2 by 2 by 2, right? A scale of 1, 2 by 2 by 2. That means we should have basically 1 as a half size on each side of this cube. So I would expect these vertices to be at like -1 or +1 on either side. And that is actually what this accessor is saying. It's saying that we have some component type. There are 24 values here, with a min of -1 and a max of 1 for the values. It is a vec3. Now, this component type might be a little bit confusing because it's like, what is this number? It's random number. But if you go look to the spec, which is one of the few things that the spec I actually find useful for, we had 5126. That is a float that is signed and is 32 bits. So we've got an F32 here. There's a couple of other things here as well. So we can say that this accessor is looking for a vec3 of F32s, and there are 24 of them, which, you know, roughly fits for the position of a vertex for a mesh. So that's how we get that data out of that bin. This isn't strictly speaking necessary for Bevy GLTF, but it's good to know like how this file format actually works. There are multiple pieces to it. It's the GLTF and the binary blob. It's not one or the other, it's both of them together. And if we look down here, this is like a vec2, which is what I would expect for the texture coordinates. And then if we look down here, this is the indices, which there are 36. And then if we look at the buffer views, because like each of these has a buffer view, right? So if we look at the positions, where are the positions in the buffer? We're looking for buffer view 0. Buffer view 0 is this index. We've got buffer 0, byte length 288, byte offset 0, and then a target number here. And this is buffer 0. It's got 840 bytes, and we're looking for about 288 of them, it looks like, at an offset of 0. So we would just read those out effectively. Now that all that code is written for us, but it's good to know how that code or how that binary stuff gets accessed. So let's get into the crate. Let's start looking at the Bevy repo. This is Bevy engine Bevy. I'm going to scroll down and go to crates. We're going to scroll down and go to GltF, Bevy GltF, and we can start right here at Cargo.toml. So we've got a Cargo.toml, we've got a source. This is just a crate, it's a library. There's not much in the README, it just labels it. Most of the documentation is actually in the source code, as we'll see. This crate actually ends up being the Bevy : GltF module inside of the Bevy crate. If you're using it individually, you can go look at the Bevy _GltF crate. But in this case, we'll be sticking with the 0.16 docs, which is notable because we're looking at the 0.17 source code at the moment. Now, I happen to know there's not much difference between the two, which is why that's fine. We could run the docs locally. I decided not to. This is a little bit easier for me, but I basically track all of the changes that are happening to a bunch of the Bevy crates all year long. So I happen to know that there haven't been many changes, at least changes that are relevant to what we're going to be talking about. So if we go and start with the Cargo.toml, this looks pretty regular. This is just a package. It's called Bevy GltF. We've got 0.17-dev as the version because we're looking at the main branch here, and we're about to get a 0.17 RC pretty soon. There's a number of features in this Cargo.toml that we'll see actually later on when we start looking at the source code. And this is mostly like PBR features. The one feature down here that's different is basically Bevy, Blender, and GlTF have different coordinate systems, and GlTF actually has different coordinate systems for some different objects. So somebody basically that uses Bevy noticed that and put in an option here to be able to do a slightly different conversion. We'll talk a little bit about this in a bit when we get into the source code. We've got a bunch of dependencies here because GLTF is, again, all of these things. It's scenes, it's meshes, it's PBR materials, and that is a lot of bevy. I don't want to say it's like a lot of the crates, but it's like it uses bevy app, for example, bevy animation because we could have animations. It's got meshes because we could have meshes. It's got PBR because we could have materials and rendering stuff. Like a lot of these meshes are going to need to be rendered at some point. So we'll want to create those resources and whatnot, and so on and so forth. Down to the probably most interesting dependency here is the GLTF dependency. The GLTF dependency is not a bevy crate. It is just a Rust crate for opening GLTF files. And they've already done most of the hard work of opening a GLTF file and converting it into a set of Rust structs and iterators and stuff that you can actually work with. So as you can see here, if we open a GLTF file using the GLTF crate, we can iterate over the scenes in the array that we looked at, or the nodes in that scene, and get the index and other metadata. It also allows you to either read or not read that binary blob, and leave some things to the user. So this particular crate doesn't do things like fetch web URLs, but it does support the GLTF and GLB representations. So if we look at this, we can say, okay, there's a number of features on this crate. Why do they exist? KHR likes punctual is probably the easiest to explain. If you're in Blender, you can see that we have a light here and a camera here and a cube here. But if you look at the data in the GLTF that we exported, there's no light, there's no camera. It's only the cube mesh, the cube material, and stuff like that. So it's extremely relevant then that the Chronos group provides a GLTF exporter that is in Blender. There's a whole bunch of extra stuff in here that we're not going to cover. This is kind of like implementation details of a Python implementation of a Blender to GLTF exporter, which is not really what we're here to do. Just note that this is the code for that if you are ever curious about how Blender turns something that is in a scene into a GLTF file, or work with it in a way that you need to debug it. So KHR likes punctual is a GLTF extension. Many of these are extensions, such as materials index of refraction, materials volume, unlit, and so on. So if we go back to our GLTF and we hit export, we click this little include here, we can say that we want to include punctual lights. This punctual lights, if you hover over it, will tell you that it actually is the KHR lights punctual GLTF extension. So if we export this, what happens is that our GLTF file gets a little bit bigger. It tells us, hey, we're using the KHR lights punctual extension. It is required for showing whatever is in this GLTF file. And then the extension gets to stick its data both in this sort of like this global area, which adds a lights array similar to the meshes, the scenes, the materials, etc. And you can see this is actually our point light. And now also in our scene down here, we've got 2 nodes as children instead of 1. So we've got node 0 and node 1. This was our cube, node 0. We now also have node 1, which is this light and has more extension data. So this extension data on the actual light node itself is just saying, look back at that other index for the lighting information. But this is the way that a lot of like extra data gets passed around, but it's not the only way. So if we look not at the other extensions here, which are mostly like PBR related extensions, but we look at extras here. Extras are the other major way that additional data gets placed, so to speak. So if we click on the object here, this is this orange little vertical navigation element, which means that we are on the cube object. Open custom properties, we click new in here. And let's say we're going to make this a string, and I'm going to make this property name, I don't know. We'll be really YouTube-y and be like and subscribe. And this will be a string. So like and subscribe, how we'll have a value of definitely, because everybody's going to do that, right? And then we get to also click in here on the mesh data. So we just clicked on the object data. And this is really important. And something that I think that people get very confused about. If you click up here in the outliner, it doesn't change what shows up in this panel down here. If you want to change between the object data and the mesh data, you have to click in this vertical space. So if we click back into the object, we can see our custom properties down here. If we click on the mesh, there's no custom properties here because it's a completely different node. So we're just going to leave this as prop 1. So we've got like and subscribe definitely on our object and prop 1 on our mesh, and we will export here GLTF include custom properties, right? So data custom properties is the checkbox that we have to check when we're exporting, and we'll hit the export. And that'll allow us to go look at our nodes. In this case, we've got our cube node here, right? which points to the mesh that it's going to use. And it's got extras here. So extras is that GltF extras. That's the feature that we're looking at in that GltF crate. And it allows us to just kind of stick in any kind of data that we want in here. This can get pretty complicated. You can actually, I think, stick full Python values in here that can serialize to JSON and whatnot. But note that the extras that were like and subscribe on the Q object are here. And if we go look at the meshes, now our other extra, our prop, is on the mesh data. So that's what these features are for. They're for the JSON representation of the GltF. We've got some extensions, which are kind of structured ways of declaring, hey, we're using this, saying whether it's required to render the scene or not, and passing that data around. And then GltF extras are things that are a little bit more user level. You can use them for anything. Skeen uses these as the way to pass data through because it takes advantage of some things that Bevy has done. For example, if we see GltF extras, there is a struct in here that we'll see in a second when we look into the source code. But this is GltF extras, and that value that we just saw in the GltF will literally get inserted here as a JSON string. This component will show up, or a similar component, we'll look at a couple more, will show up on your entities that have this extra data on them. And then you can parse it and do whatever you want with it, which is very cool. We've got a bunch of other crates here. None of them are super interesting. You know, percent encoding, iter tools, tracing is used everywhere in Bevy or Bevy log. And then like it's part of a workspace. So that's about it for the Cargo.toml, which means that we can get into the source at this point. So let's go source. Let's go, well, before we go lib, let's take a look at the source directory. So the source directory has loader, a couple of other files here, assets, convert coordinates, and label, as well as vertex attributes. So if we take a look at lib, this file, because I happen to know, has all the documentation for the plugin. It defines these other modules. And you'll notice that there wasn't a loader module in the root, but there is a module here called loader. We'll talk about that in a second. We've got a very common pattern here called a prelude, which is taking some of the structs that are defined inside of this crate and exporting them. So if you were going to use Bevy GltF on its own, you could do use Bevy GltF : prelude : star, and you would bring these three items into scope. That's what this code is doing. We're also hiding that from the documentation because this tends to be used as part of the Bevy crate. So these are already going to be documented in different places. We also have a default GltF image sampler here as a resource. So if you are unfamiliar with what an image sampler descriptor is, this is basically just storing a default version of that. So if we go to Bevy, we can search this literal type, click on it, and this will show you what it is. This is basically saying what happens if you try to sample outside of the UV coordinates. The address mode can be something like clamp to edge, which will clamp to the color that is on the edge if you go move past it. You can repeat or mirror repeat. This can be really good for repeating textures or scrolling textures. And then there's a couple of other things like mip-map related, right? How should you actually filter? Because sometimes you have these textures, they're on meshes that are tilted away from the camera, and one screen pixel doesn't necessarily correspond to one texture pixel. One screen pixel can, like if you imagine yourself shooting a ray through the screen, it can hit multiple texture pixels effectively. That's not really what's happening. It's a decent enough explanation for a TLDR for the moment. I have a separate video on mip-maps that I'm working on, so if you're interested in that, wait for it. But that is setting up the default image sampler. So there's going to be textures that are probably used in most GlTF files. Which image sampler should we use if there isn't one available? This is setting up that image sampler effectively. We do impl on default GlTF image sampler with like some creation of new and whatever. Not super important here, nothing really interesting. These are wrapped in an arc mutex, but that's not really relevant for why we're using them or whatnot. Then we've got the GlTF plugin. This is part of the default plugins for Bevy. So you don't actually typically set this up, but if you're setting up something like custom vertex attributes, which we'll talk about in a bit, you will actually end up setting this yourself. So we've got that default sampler. We've got the convert coordinates, which we talked about a little bit before. The image that I like the most for describing why there are coordinate differences, but the fact that there are coordinate differences and what they are, comes originally from Freya with an addition by IS, who has added Bevy onto the visualization. Also, Unreal recently declared that they're moving away from ZUp, so they are no longer going to be in this bottom left coordinate, which nobody else joins them in. But you can see Blender in this bottom right and Bevy in the top right. Now, GlTF isn't on here, but suffice it to say that there are differences. If you're working in some program and you export that to GlTF, there's a coordinate conversion. And if you import it into Bevy, there's another coordinate conversion, which is roughly what this is trying to address. Basically, this coordinates, or this convert coordinates is new, or it will be new in 0.17, and will allow you to, as far as I'm aware, basically rotate your models 180 degrees. There's a little bit of discussion about what this is going to finally look like in 0.17, so don't take this as the source of truth for what this convert coordinates flag will actually be doing, because more PRs might get merged before the release candidate actually ships. And then we've got custom vertex attributes. Custom vertex attributes, if you've never seen those, are available in the Bevy repo to look at. So if we go into the Bevy repo and we scroll down to examples, there's a couple of examples here. One of them is going to be in shaders. This is going to be not a GlTF example, but it'll be the custom vertex attribute example here. And this will show you how to create and take advantage of a custom vertex attribute for a custom mesh, or for your mesh that you created with Bevy. In this case, we've got the blend color attribute. This is being defined as blend color with a format of a float 32 by 4, which is a vec4 of F32s. Then when you create the mesh from your cuboid, you can do it with an attribute. This is our custom attribute. In this case, it's a vec4 that is like reddish, or like very red, basically. It's like only red, no blue, no green. I just reversed those, RGB. And with an alpha of 1, and there's 24 of them. So basically 1 for each vertex. That's why it's called vertex data. It's one piece of data for each vertex. And you can run this example if you want to, and there's a shader associated with it. But this also, if we go into the 2D directory, has a custom GlTF vertex attribute. And this shows off how you would set, it doesn't show how it would do it in Blender, but you can set additional vertex attributes in Blender that you then export with your data. If we go and we look at Blender for a second, and we check this export, and we look at data, we can go into mesh here, so data mesh, and there's a bunch of additional data here. Sometimes you need the tangents, for example. And if we wanted to export the vertex tangents or any other attributes, we could click these and get those additional attributes. And if you set up your custom vertex attribute here, you have to tell the GlTF plugin about it. Or you don't have to, but you know, like you probably should if you're going to use it. So you get the GlTF plugin and you add this custom vertex attribute. In this case, it's barycentric. In the other example, it was blend color. But this is how you get like custom data associated with your vertices, and you get access to that in your shaders to do whatever you want with it, right? So you don't necessarily want to use vertex color because that impacts the color if you're using standard material, for example. But if you want to do a standard material extension and you want to paint some data onto those vertices inside of Blender, you can totally do that and use a custom vertex attribute. And that's what these are. These are the custom vertex attribute definitions. So we end up with this GlTF plugin. We've got a default sampler, we've got our custom vertex attributes, and we've got whether we're going to convert the coordinates in a specific way or not. This is mostly GlTF plugin setup. So if you're not familiar with registering types, if you don't use reflection that much, this is basically registering a bunch of types that are defined inside of this Bevy GlTF crate so that the Bevy type registry is aware of them. This is useful for a number of different things. It's also just kind of a best practice to register types that you're going to be using. This is also required for things like Scheme, which lets you write component data inside of Blender and then uses the reflection infrastructure to actually instantiate those values. Your Bevy app has to know about those values in some way to be able to reflect them. So here we can see GlTF extras, which we talked about earlier. There are others like GlTF scene mesh and material extras. It may look a little bit weird that we have like GlTF mesh name and GlTF material name. And also, why are we splitting out like extras into these additional positions? And the answer is that the entity that this mesh is going to be on is the same entity that this material is going to be on. So theoretically, if we have a custom property on this mesh, right, a GlTF extra attribute on this mesh, and if we looked up at our materials, you can see that there's another extras here. This is some random Blender extension. It didn't add any data, but it still has a representation because of the way that Blender requires plugins to handle their data. But you can see that it's empty very clearly. But we could put extras in here, right? And this is like human authorable too, right? Like if I wanted to, I could just modify this, say this is going to be prop 3, right? So this material 1 at index 0, and this mesh, what do they do if both of them have extras? This is why we have these different types, because a mesh and a material can both have extras. If they're both going to end up on the same bevy entity, what do you do with those extras? And keeping them separate in different types is a valid approach. And then we register the asset loader, or pre-register rather, the asset loader for GltfLoader, which gives us the GlTF and GLB file extensions. And finally, we have finish, which if you're not familiar, we can go right to the docs, search for plugin, click on plugin, and this is a trait. This is the trait for how you implement a plugin in Bevy. On the left-hand side here, we can go find the finish function and finish adding this plugin to the app. Oh, well, I wouldn't have guessed that. Importantly, it's once all plugins registered are ready. So once all plugins that are registered are ready, this function gets called on those plugins. So if you need to wait for another plugin to do some asynchronous setup like the renderer, or something that needs to insert resources or something like that, this finish function is super useful. What does that mean? Basically, when we run finish here, we want to get this resource. This resource, if we close the sidebar here and take a look, at the top of the file, it's coming from bevy image. So this is obviously a resource that's getting inserted by bevy image that we are looking for after everything has been registered. And in this case, we want to get the supported compressed formats from the bevy image crate. And if we can't get them, these crates are all very like individually useful. So if you wanted to, you could take a bunch of them and put them together and try to make something work. And maybe that doesn't go right. So that's what this warning would be telling you. Like, hey, the resource wasn't found. It kind of needs to be here if you're going to use compressed images. And then there's some additional stuff here. And we finally actually register the asset loader with our custom vertex attribute, the supported compressed formats for the images, the default sampler for those images, and this coordinate conversion flag. So that's all of the plugin setup. That's a plugin configuration that lives in lib. Now, we talked about the vertex attributes. It's worth just taking a quick dip into the vertex attributes while we're here. In this case, there's a number of structs here, including like normalization. This is defining whether data types require normalization or not. If you're unfamiliar with normalization, one of the easy examples I can give you is if you have a vec that is like a vec3, let's say, of 42, 72, 80, right? XYZ. Doing certain kinds of math on that value is easier if the length of that vector is 1, right? It's a unit vector. So if you normalize it, it will become a length of 1, but it'll point in the same direction. This is what a dir3 is compared to a vec3 inside of Bevy. So normalization is super useful in various cases. We also define some error cases. So if your vertex attribute data is malformed, this uses this error to define these. This error is pretty useful crate, honestly. So right at the top here, you see this error. This is that derive that we're looking at. And it defines some error types with some useful attribute macros for making it less verbose to define. And then we looked at those buffers earlier. Part of the reason we looked at those buffers and why we talked about accessors at all, even though, you know, how often are you going to think about an accessor, is because there's code here is meant to access those buffers. It's meant to access the data inside of them. So this buffer accessor takes one of those accessors. It takes the buffer data and the normalization, whether you want to or not, and it defines some functions for accessing that data. Because remember, these buffers need to be read from like at offsets for specific ranges. So these are kind of helpers to do that. This next bit, enum vertex attribute iter, is actually really interesting, I think. You can see that inside of this, it's GlTF accessor iter, you know, F32, U32, a two-dimensional array of F32s, and so on and so forth. This kind of pattern, if you've never seen it before, is the pattern of kind of like taking an enum and wrapping a bunch of very similar, but not exactly the same types so that you can return one of them from a function. So if we can return the enum from a function, we can return any of the individual values. Either is a crate that takes that and makes it kind of robust. So if you think about an optional type or an option type, which has some and none, or a result type, which has okay and error, those indicate some kind of success. But this enum either doesn't. It just has left and right. It's not success or failure. It is just left value and right value. And that's what we're seeing in that Bevy code. This is an enum with a variant that wraps some value on the left and some value on the right. What's really interesting about this is that in certain cases, you can define helper functions on this, like wrapping either type, and do things like if left and right actually do the same thing, then give me the iterator back of whichever one I have, right? Without needing to know whether it's a left value or a right value, you can just call into iter and start iterating over the values. So like if they both produce F32s or, whatever. So this is a pretty useful pattern. This is also used quite heavily in leptos code if you've done web work with Rust. And here it's used to kind of stock all of these different iterator types together. Moving on from that, it's basically just a bunch of matching on these various vertex attribute values and doing slightly different things based on that. So like vertex attribute iter F32, collect into values float 32. Not terribly interesting code, but a lot of, matching. So that supports the custom vertex attributes in that file. There's not too much to it. I think the most interesting piece of code to check out here is actually in loader. So if we go into loader, Bevy uses kind of an older convention, which is using mod.rs files. So if we go back up to the source, you can see that most of the modules are like assets.rs and convertCoordinates.rs, but loader is a folder and it doesn't have a file. So Bevy uses this mod.rs convention. This would have been the loader.rs file up a directory, but this is the same entry point regardless. So if we go and we take a look at this, we can immediately start seeing that this is gating certain features based on whether they're enabled or not. So remember, GlTF has quite a bit in it. In this case, if we have the Bevy animation feature enabled, then bring some things into scope. There's a GlTF error again with this error here, and there's a number of different ways this can fail. If you've never seen this error or something like snafu, definitely go check those out because they're super useful. You can either say, hey, if we have an IO error and we're using a question mark, then automatically implement from an IO error into this slot right here, which is really nice. So we've got our GltfLoader struct here. We've got all of the configuration that we saw before, same stuff, supported compressed formats, custom vertex attributes, the default sampler, and whether these coordinates should be converted or not. And then we've got some more GltfLoader settings. And this is kind of relevant. The reason we went over extensions earlier without seeing them in the code first is that there are some configurations here like load lights. So if true, this loader will spawn lights for the GlTF light nodes. And this comes from that additional checkbox, that additional KHR, punctual lights for those point lights. There's also cameras. We can export cameras using another checkbox and so on and so forth. These render asset usages to find whether these like meshes of materials are going to be used in the main world and the render world or one or the other. If you've never seen that before, don't worry too much about it. You can definitely go check it out in the docs, render asset usages in the Bevy docs, just like we were doing before. And there's some default values here and whatnot. And then we move into the GltfLoader, which is like the meat and potatoes of this whole crate. So we're going to take this load GlTF and we're just going to collapse it for a second, because I think the more interesting thing here is the AssetLoader implementation. To start with, this is where I would dive in before looking at the load GlTF function. This is the definition of the asset loader. So if you do like asset server.load with a path, you end up using this asset loader implementation for GlTF and GLB files. Those extensions are defined here, although they are overridable. And then this load function gets called. So we get a reader, we create a vec, and we read into that vec. Then we call our load GlTF file. We call it with this load context and the other settings and whatnot. Now, before we go look at the load GlTF file, there's a bunch of additional helpers here. None of them are particularly like terribly interesting to go into and read, but there are helpers for loading images, loading materials, loading the nodes that we talked about, loading those buffers from that .bin file, which is why this is async, right? If it has to go out and fetch that additional bin file to load those buffers in, then it has to do so. And we make it all the way down to the tests. The tests are really interesting. I think if you're interested in how Bevy handles GlTF, these kinds of things can be really nice to go take a look at. For example, here's a single node test that says, okay, we've got a test.gltf file. We've got this helper function that pretends that this GlTF path contains this data. In this case, we've looked at a GlTF file already, so you should be able to read this, right? It's a GlTF v2. It's got some nodes, it's got scenes. So the default scene is scene 0. Scene 0 is this scene. It has node 0 as a child. This is node 0. So we should expect that this test is doing something like testing to make sure that the test single node component is on this entity. And if we go down to this test, we can actually see that that is actually what is happening here. So if we go into the GlTF root itself, the named nodes contains key, test single node, and so on and so forth. So if you're interested in some of the more nitty gritty of the handling of these kinds of things, the test can be really great to read through. We're gonna not read through the rest of them and go back up and take a look at our load GlTF, because that is the meat and potatoes of the crate. This loader takes our GltFloader that we talked about earlier, the bytes for this GlTF file or GLB file, the load context, which is an AssetLoader thing that lets us do sub-assets and things like that with some more settings. So we get those bytes, we turn them into a GlTF using that GlTF crate that we saw earlier, and now we have a GlTF, right? We have all the Rust struct representations. We try first to convert this into a string slice. If we cannot do that, then we have something that is like invalid UTF-8, right? And then we can't actually access this this file. We load the buffers in here. We get the textures here from the GlTF document. If bevy animation is enabled, then one of the things that we really want to do is go through and find all the bones and get their names, because GlTF and Blender and some applications like them don't have unique IDs for the nodes in the data. When we look at our GlTF document here, there are no IDs. There's no like way of differentiating them from each other other than like by index, right? And by index can kind of change per save depending on how things get saved out. So if you're talking about animations and you want to say access a different bone or target a bone for an animation, one of the ways that you can try to make that a little bit more robust is, let's say we have an armature where the head is kind of like just below the root, and then you've got neck, chest, like knee, foot, right? So the name of the head would be like root head, and the name of the foot bone would actually be root head, neck, chest, hip, knee, left foot. And that's what this get paths call is doing, our collect path call is doing. It's bringing all of those names together to create kind of like an ID that we can use to be reasonably sure that this bevy animation is going to target the right bone. Moving on from that, this convert coordinates, we talked a little bit about this. If you run any 0.17 based bevy application, you'll probably see this warning if you load a GlTF. This is where that warning comes from. Moving on, we've got some more bevy animation gate, and this actually is where we see the pattern that develops for the rest of the file, the rest of the load GlTF function. We create a couple of resources here, or not capital R bevy resources, but just a vec and a hash map. The vec here is just a vec of all the animations. The hash map is a hash map of string, or rather, it's actually box string, but it's a string slice to animation clip, or handle of animation clip actually. And we go through and we find all of the animations, we iterate over them. For every channel, we set up all of the interpolation and things like that. We're not going to get too deep into like the nitty gritty of like animation here, because we're just talking about the bevy GlTF crate. But we go through all of the things that we need to, we iterate over them, yada, yada. We grab any curves we need to, we grab the keyframes that we need to. And that is, you know, all of this kind of code that I'm scrolling through right here for doing that in various different ways with different curves, with different samplers. You know, you can do like a linear interpolation or a stepped interpolation. And finally, we get down here to load context.add labeled asset. This is really important because this is how you end up with those nice imports that are like GlTF asset label animation 0, right? If we go back to the bevy repo for a second and we check the examples, we go into the animations or something like that. I think animation graph probably doesn't have it because it uses a RON file. Oh, it does. Here we go. So it does it only for the scene, right? So GlTF asset label scene 0 from asset, and this is our GLB. So this is looking for the 0 indexed scene inside of that GLB file. And you can do this for animations, you can do this for a whole bunch of things. If we look for GlTF asset label, this will actually show you the enum for all the things that you can look for. Same things we've been looking at: scene, node, mesh, primitives. It's worth noting that a GlTF mesh is not a bevy mesh. A bevy mesh is closer to a primitive, a GlTF primitive than it is to a bevy mesh. Sorry, closer to a GlTF primitive than it is a GlTF mesh. So the primitive is like the bevy mesh. The GlTF mesh is something slightly different. And then we've got animation down here, for example. So this is how that gets set. So load context, add labeled asset, defines the label, and turns this into a string. These can actually be specified as strings. We can actually see that if we want to go into this other file very quickly, right? If we go back up and we go into label, label.rs actually has all of these things and also has all of the string representations, which if you've been around Bevy for a little bit, you might have seen these string representations instead of the more typed variants. And then we push all of those into the respective vex and hash maps and just keep them around for later. We'll see why we keep them around for later. It's not that interesting. We just stuck them in the GlTF struct, but we keep them around to do that later. And then the same thing for everything. This is for textures. The interesting thing about this part is it has to happen differently based on whether we are on WASM or not. If we are on WASM 32, which effectively is synonymous with a web deployment, but that isn't strictly speaking true. There are other WASM targets that are going to be more interesting moving forward, but it's all WASM 32 at the moment. And if we are on WASM, we need to do an IO task pool with some scope. Otherwise, we can just do whatever we want on native. Same thing for materials. We get materials in a vec and named materials in a hash map. We do the load materials. We call load material. We get them. We insert them. Same thing. Same thing for meshes. Same thing for et cetera, et cetera. So all of this is kind of just doing that work of grabbing the things from the Rust structs and shoving them into different vecs so that people who write Bevy apps can have a nice experience. This includes things like any nodes or named nodes, named skins, bones, all those things. And finally, it does check for cycles at this point. This is because like your GlTF doesn't need to come from Blender. Like you could write it out yourself if you really wanted to. Or you could write it out from another application that maybe isn't as well behaved. So like we want to check for cycles to make sure that we don't just loop forever. And then all the nodes get populated. You can see talk of joints here, but it's not super interesting code. It's not like difficult to understand code. It's like node mesh, over the mesh, get the index, and then get that, and then clone it. Right, and then we have the mesh. We've got some more Bevy animation gating. We've got some more add labeled asset for different things. And then we finally get to the scenes. And there's something interesting about scenes compared to all of the other sort of loops that we're going over to load all of these things. And this is that scenes have their own world. So if you're familiar with Bevy at all, you know that there's a main world and a render world. There are also a world for every scene. And this is particularly interesting because if you start spawning scenes, right? If you've got a handle to a scene and you spawn that in and it has entities 1, 2, and 3, and your main world in your Bevy application also has entities 1, 2, 3, and 4, how does that work? And the answer is map entities. So those scenes get mapped in as entities 5, 6, and 7 inside of your Bevy application. This is basically hash map lookups. It basically says, okay, we've got these 3 entities over here. We need 3 entities over here. Change their IDs, make sure they don't collide. So we end up in that world. We end up, getting all these things into that world and spawning all of these nodes and stuff in that world with all the relevant data. You can see here that we've got our GlTF scene extras getting inserted here. That's our extras that we were looking at in the GlTF. We've got more Bevy animation gating, inserting animation players anywhere there needs to be one on the animation routes. And right here down at the bottom, after we're done with all of that, after we're done with setting up all the scenes, we end up setting up this GlTF struct with all of that data. So if you look for the GlTF asset in your Bevy application, this is what you get. You get all of those things that were all loaded and processed, created, the scenes with their own worlds, the animation clips, everything ends up here. So that is pretty much it for all of the code here. There are other files, right? Like we talked about GlTF, we talked about GlTF mesh. These are just kind of like Bevy namespace wrappers because Bevy already has a mesh that isn't the same thing as GlTF's mesh. And those all exist here and whatnot. So that's Bevy GlTF. It is basically just responsible for loading all this stuff in, creating all the nice assets, or rather all the handles to all of the things that you would want to that come out of that GlTF file. Hopefully you understand a little bit more about what these GlTF files are, what they look like, what data gets included in them. And we might be doing this again for another crate, maybe one of the bevy crates, maybe something else. If you have any questions about GlTF or the bevy GlTF crate, please feel free to keep the questions in the comments, and I will try to respond to them. Otherwise, I will see you in the next video. I hope you have a great rest of your day.